Thanks for the invitation. My name is Gabriel, and for the last year, a little bit less than that, I've been working as an associate professor at the Marine Bioprospecting Group of the Center for New Antibacterial Strategies of the Arctic University of Norway. So it's the northernmost university in the planet. So it's a very nice place to be, very, very beautiful and very different. But before going there, I was in Lotarina's lab, who just spoke to us. So the data I'm showing here is mostly what I've done in her lab before moving, switching jobs. But before, just a very brief idea to you about how phages are in Norway nowadays. So there has been a lot of interest in phages and phage therapy, especially because of this report that was written to the Prime Minister saying that phages and phage therapy are the likely solution to the antimicrobial resistant crisis. Then there's a well-known company in Norway who already sells phage products for aquaculture use. And then there at the lab, I'm trying to establish a phage research group, actually a viruses of microbes research group. And we're getting our first phages from the Arctic and starting to characterize them. So I hope to get them more nicer information later this year about these new phages. Okay. So here, yeah. Just need to. Just tell me which one it is. Is it this one? Yep. Yeah. Sorry about that. Okay. So that's great. Yeah. Okay. Yeah, but then going to the topic of this talk, which is phage bacterial interactions in mucosal conditions. So I guess I cannot change the slides now. Okay. Now I can. So I guess that's what bridges what I was doing in Lotarina's lab and what I want to do in the future. And it's my main focus is prophylactic phage therapy. And it's tightly related to the bacteriophage adherence to mucus model, the BAN model. So if you think about a phage and a bacterium, how they interact in the environment, it's very unlikely that one finds the other because you need near atomic distances for the ligands and the receptors to interact. So it's very likely that there is a lot of the adaptations around that increases the chances of encounters somehow. And this BAN model explains one of these adaptations. So the idea here is that some phages, at least, they can interact with mucin fibers, gravitate around these fibers. And by doing so, they get held in the mucosal layers, and they stay there waiting for the host to arrive. And it's a symbiosis between phages and animals because the phage gain by increased encounters with the host, while the animal gains from protection from the phages. So it's a win-win situation for both of them, but not for the bacterium. And in Finland, when they started there, we started to speak about this model, and we decided to test this in a natural infection system. Because so far it has only been shown in vitro with 24 E. coli, and we wanted to see that in a real infection situation. So for doing so, we use a Phylobacterium columnare, which is a fish pathogen. It causes mucosal diseases, columnaris disease in freshwater fish. It's a huge problem for aquaculture in Finland and other Baltic countries. We had rainbow trouts, our animal model, and a large collection of phages against this bacterium that were in the lab. So that was kind of easy to validate our findings. And we started by checking whether other phages could also bind to mucins in vitro, because so far only T4 was shown to do that. And we tested a different collection of the phages in the lab, infecting different hosts. Even flip is here, like the topic of previous talk. And we saw that most of them could actually seem to be retained in mucin-containing plates when you compare them to conventional plates with no mucin, showing that there's an indication that these phages were actually being held by the mucin in the plates. Then we moved to see if that also happened in vivo, because of course the mucosa layer in a fish is completely different from agar plate with mucin, because we have the mucus shedding and we have the microbiome and everything. So we designed this experiment in which we exposed the fish with a high amount of phages in flow-through systems, just at time 0 that we gave the phage. And then over 1 week, we're following the phage titers on the mucus and on the water. And you can see that on the black triangles here, which is the mucus samples, we can consistently find the phage over 7 days. So the phage is staying in the system, while in the water it's more random. So it shows that actually the phages are being held in the mucus of the animals and not stuck in the aquarium or floating in the water or anything. Then we tested if this phage retention would be relevant for protection. So these graphs here are survival curves in which we exposed fish to a little dose of Bacterium columnare. And the controls like no phages in black here and here. And then the color lines are fishes which have been exposed to phages beforehand. So for 1, 3, or 7 days before the bacterium. And you can see that if you give the phages before you give the bacteria, you have some degree of protection and also some higher survival, showing that the phages attached to the mucus are actually protecting the fish, even if they come before the bacterium, days before the bacterium. And then we started to wonder whether the mucus or the mucin would affect the bacteria alone. And then the answer here is yes, it affects. So it's not a big novelty. There's also publications about that. But we could see that if you expose columnare to mucus or the mucin, we can see the formation of biofilm, protease secretion, increasing chemotaxis. But more importantly, we saw that the bacteria is more efficient in killing fish if you expose it to mucin beforehand. So mucin is preparing the bacteria to cause disease and to invade into the fish. And finally, on the sense, we also look at the dynamics between mucus, the mucin and mucus effect on the phage bacteria dynamics. And for this, we have exposed bacteria to mucin or mucus, and then we affected the bacteria compared to the controls. And that was interesting because important note here is that this phages, sometimes they are very hard to grow in liquid. For some reason, they don't like to grow in liquid cultures. But if you provide the bacteria first, before the infection, if either primary mucus or if purified mucins, you can see that the phages grows nicely as they were expected to do. So the phages are somehow exploiting the changes that the mucin makes on the bacteria to be able to infect better that bacterium. We published this data in Bio a few years ago. But if you think about what I spoke so far, it's too biased towards the phage. So it means that it seems that the phages are always winning. So it's staying in the mucosal layer and it's protecting the fish. So the bacteria has very little chances here of doing something. And we started to think about how could the bacteria invade the mucosal layer and escape these mucosal-associated phages, because they likely are doing that. And for answering this question, then we proceeded to do more experiments. And we designed this large scale experiment that lasted for 4 months. So for doing that, we mixed the bacteria and the phage in cultures, containing different nutritional conditions. So lake water alone. So here the bacteria doesn't grow, but it stays alive for a while. Or the culture media we commonly use for this bacterium. And these 2 conditions with mucin added to that to simulate mucosal conditions. And what we did was that over 4 months, we are sampling every week. And every week we'll check several parameters. So the titers of the phage and bacteria. We would isolate bacteria for later studies for immunity. We're checking morphology. We're checking the acquisition of spacers in the CRISPR regions. Trying to understand, trying to see if these different conditions would change a little bit how the interactions were happening. And the major results from this work is that, first of all, the bacteria in the phage, they survive to the end. So they have been added on day 1, and then they stayed alive until the last day of the experiment. So when they are together, they tend to interact after all this time, of course, changing, but they're interacting actively. And the major finding of this work was that when you compare spacer acquisition on these different conditions, you can see clearly that on the lake water plus mucin condition, around half or a little bit more than that colonies that we tested were positive for new spacers in the CRISPR leucide that this bacteria has. So this means that having the mucin in lake water is heavily affecting the decision that the bacteria has on being immune to the phage or to try to evade the phage. And the way the bacteria do it here is by activating this CRISPR-based immunity. And there are some reasons for that. So lake water plus mucin is the condition that the bacteria is likely finding when it's trying to infect the fish. So it's what makes it change from the environmental state of life to the pathogenic way of life. So that's the signal that the bacteria has to change. And we have seen before that activates a lot of virulence factors, which is expected, so more chemotaxis and so on, but it's also activating the CRISPR system. And it's interesting because that's, by doing that, the bacteria can then keep all the virulence factors intact, but be protected from the phages by having the CRISPR immunity active. Because if it changes morphology, for example, which is very common for the species, what's happened is that then the bacteria loses virulence. And on the infection model, that's not too good for the bacterium. So that was our main finding here. So for closing up, our conclusions here is that mucosal-associated phages, they have potential to protect animals from invading bacteria. So it's something that we must consider nowadays, that the phages can be retained in the animal or in our bodies, and that can lead to protection. We have seen that phage-bacteria interactions in these mucosal conditions can differ from normal culturing procedures. So in this case here, for example, if you have mucin in the cultures, then you can grow the phages in liquid, which doesn't happen if you don't have mucin around. So that can even have some applications for growing phages, for example, in vitro. We saw that the environmental conditions, in our case, the mucosal conditions, they affect the decision of phage-resistant mechanisms. So that's also relevant if we're studying this mechanism in vitro, because maybe if you're missing this eukaryotic signal, you might not be seeing the mechanisms the bacteria will decide to use in a real infection system. And finally, we saw that the bacteria has developed strategies to evade the ban model. So even though before the model seems too biased towards the phages helping the animal, now we see that the bacteria can evade that somehow. So there's a lot of clinical and ecological implications. And this work has been published here this year. So we are very happy with this publication. And I think that there's a lot of surprises yet. So if you keep looking into that, maybe you're going to see ways that the phage is invading the bacterial evasion, because of course that's how this host pathogen evolution, coevolution processes happens. So they are all the time helping one to overcome the other. And where to go from here? So based on all this that I spoke, of course, the specific details are on the papers. I just highlighted the main findings here. And we always been thinking about expanding this to other pathogens. So move from the columnarium model to other things, and then find more mucosal-associated phages. And that's something that's been happening. So if you think about the mucosal environment, I can highlight maybe 3 different phenotypes that we're interested in checking. So one are the phages binding to mucin from the phage side in the mucosal environment. So you might have this selection pressure that at least some phages, they are getting better in sticking to mucus and staying there waiting for the hosts. From the bacteria side, you can think that the mucosal environment is upregulating the virulence factors and also CRISPR immunity, so that the bacteria gets ready for infecting the animal at the same time that it starts to be prepared to evade phages, the phages are there. And of course, we have all the pressure from the immunological point of view of mucus that the bacteria must also deal with, that if you think about the animal itself and not the phage. And when we look at the phage bacteria together, then we are interested in this improved phage growth in mucin-exposed hosts. So at least some phages, they are more efficient in killing bacteria if the bacteria is ready to infect an animal. And that can be something exploited for phage therapy, for example. And we've been slowly checking other hosts, and we have some papers to come out soon about other systems. So that's better to be discussing in the future. But what I can say is that we'll be finding new targets for each one of these 3 phenotypes. So it's not related to columnar itself, it's more widespread as we expected. And something that we also want to do is to describe the mechanisms behind these phenotypes. And that's something that is still a mystery, like how bacteria senses the mucin and how mucin affects, activates CRISPR immunity and so on. And that's something that we still need to do, so no answers on that. And my ultimate goal, I guess, with all these topics, would be to focus on the revival of phage-based prophylaxis. So I say revival here because it's not something new. And we know nowadays that, for example, doctors in Poland, they're using phages in the 50s as the first liquid given to newborns. And the idea they had there was to protect the newborn from deaths associated to diarrhea. And the descriptions from the time say that it was very efficient to hold a lot of outbreaks and protect a lot of infants. And also from the Soviet side, they have a lot of experience on phages. They've been doing these mass experiments on prophylactic phaging, some including several 100,000 people, some including even different towns. So they will have phage-treated towns and phage-untreated towns, control towns. And when you take all these studies into account, you see that the conclusions is that the phages can stay in the body for 3 to 5 days, and phage-treated populations have better outcomes or less infections from bacterial diseases. So it seems to be something that it's effective, it's safe, and it might be completely related to these mucosal interactions. So by having this mechanism well described, maybe you can use that to design new clinical trials or new experiments to try to revive this and bring this back to our own reality nowadays. So that was what I had to say to you. Here's my contact, and I'm free for questions now or afterwards.
Hello, my name is Nina Molin Højland Krogsbo from the University of Copenhagen. So that's a really interesting link between mucin and CRISPR-Cas adaptation. So I'm wondering, since mucin has a large amount of threonine, and threonine is a precursor for certain quorum sensing molecules. And we also know that quorum sensing activates CRISPR-Cas. So I'm curious whether you have looked into whether the mucin increases quorum sensing and in that way leads to increased CRISPR adaptation.
Yeah, no, we didn't. So we didn't explore further than that 4 different conditions. But what we had there is that it was very peculiar on the lake water and mucin condition. So on the same concentration of mucin, but other, like let's say culture media, you don't see the CRISPR activation. So for me, it's more like mucin activated something directly related and not affecting quorum sensing. Or so might be, but we don't have an answer to that yet.
Hi, my name is Ville from University of York. Very good talk. I was just kind of wondering, how can you differentiate if these effects are like mucosal adherence of the bacteriophages, or if they're just like bacteria, maybe they're using the mucus as a nutrient, so it changes the physiology of bacteria, making them more susceptible to the phages. I was kind of thinking, how would you design an experiment to disentangle these two things?
Yeah, we have some tests with columnari and also in other species that we also measure bacterial growth on the mucin conditions. And we don't see that large difference between the mucin-treated and non-mucin-treated bacteria. So it seems more like it's physiological changes and immune regulation than actually having more bacteria there. And we have been very careful with that. We have been testing different MOIs and different conditions to show that the bacteria is not only eating mucin, then growing better, and then the phage is growing better because of that. It's more like physiological than just number of hosts to infect.
Hi, great talk. My name is Daniela. I was wondering, when you do these experiments with mucin and seeing how bacteria respond to it, are you using mucin taken from the fish? So is that from the fish, or is this externally acquired mucin?
Yeah, so most of these experiments are done with porcine mucin. You can buy it from Sigma as powder. And it's convenient because you just measure and have precise the amount of mucin you're using. But we validated everything using primary mucus from fish. So even though you cannot control the concentrations of mucins in the primary mucus, you see the same phenotypes. So you see the same responses. So we kind of think that it's the mucin glycoprotein, regardless of the type of mucin or the ratio between types of mucin, because we can see this difference between the two species. But of course, we really want to, at some point, check the specific mucins and how they affect that precisely, because definitely we can see might be able to see some differences on bacterial response.
Yeah, definitely. And one more question. You mentioned that you were interested in finding more phages that interact with mucus. I was wondering if you had any ideas of how you're going to approach that, because that can be challenging, I imagine.
Yes, until now, I guess we're just testing phage by phage, which is very time consuming on these in vitro assays. But I've been talking to some friends that they deal with AI and bioinformatics to try to use everything that we have validated in lab so that they can try to predict from the genomes if they bind or not. And the point is that we know some proteins which are mucin binders, like the Hock protein 24, but some of the phages that we tested that are positive for mucin binding, they don't have the Hock-like proteins. So likely there's other domains in the capsid that are doing that, but we don't know all of them yet. So it's still a big mystery of how to predict, and we're just doing the one-by-one approach so far for now.
Great, thanks.
There's a question online from Janet Neal.
Yes, a very similar question from the previous person who asked the question. And it's a very interesting observation you've got there, because we have also tested phage therapeutic ability in different cell lines with different mucin producing capabilities. And we could see that those producing mucin have very more activity than those. So I'm just asking whether you think mucin is something that can be explored to enhance phage therapy?
Yeah, my idea is to focus on that, not the mucin enhancing the phage therapy, but we're using our knowledge on this phage bacteria interaction in mucosas to find the best phages for phage therapy. So, and it's clear for some species that we tested, we have some phages that clear are affected and some that are not affected by mucin. So it means that it can become a new parameter to check the phage collections, and then you can use these phages in different conditions. So you can have the conventional phages for other purposes, but you can use the ones that bind to mucus to protect phage patients, for example. So I guess there's a lot to gain there for these interactions.
Hi, Gabriel. Great talk. I'm Franklin from the University of Southampton. I'm particularly interested in knowing, you said that you have a CRISPR activation because you have this high mucin environment. You've made an experiment where you are doing lake water plus mucin, a phage challenge, and you see CRISPR species being added. I was just wondering, if you looked into self-targeting spacers, if you take out the phage challenge, would you expect that actually the CRISPR system will be lost? Have you looked into that?
No, the closest we have is sequence of some of these isolates and also sequence of some of the arrays. And we see that the great majority of the spacers are against the phage. But it's a good question to see if the same activation would happen without the phage presence. But actually we have the pilot experiment that we did that, and we couldn't see any. So we thought like if you just put the bacteria and the mucin, nothing has been happening there. So maybe you still need the phage together to complete the activation. Yeah, but it's best to check that. Yeah.
Last question.
Hi, I'm Jacob from the University of Southampton. It's a really good talk, thank you. You've checked and seen that CRISPR's upregulated, but have you thought of looking at other defense systems to see if it's a generic upregulation of antiphage systems or specific for CRISPR?
Yeah, so we checked both that we knew this bacteria had. So it's the true CRISPR loci and also morphology. So this bacteria changes morphology as phage protection mechanism. And when you compared both, you see that the morphology was kind of all around. So it was just not random, but happening as it should. But to have this enrichment of the CRISPR on that specific condition. Of course, it might contain different systems, like we've seen today, there's a lot, but we didn't have this data. So for this bacteria specifically, so far we only know about the CRISPR and the morphology changes.
Thank you.
Okay, thanks.
Thank you. I'm sure we could go on for a lot longer, but thank you very much, Gabriel.